Hello, everyone. I am Jixuan Liang from Lab at the University of Hong Kong. Today, I am excited to introduce our CVPR 2025 paper, DexHandDiff, Interaction-Aware Diffusion Planning for Adaptive Dexterous Manipulation, developed jointly by HKU and UC Berkeley under Dr. Ding, Professor Luo, and Professor Tomizuka. First, let us briefly review diffusion-based planning. Methods like diffuser treat an entire trajectory as a trajectory image and iteratively denoise from random noise to a coherent sequence of states, generating smooth motions without requiring a fixed rollout. However, directly applying this to a multi-finger hand interacting with objects leads to serious issues. First, action-only diffusion models, like diffusion policy, produce smooth actions but lack explicit state coupling. When object interaction changes, these models fail without retraining. Second, state-based diffusion models, such as decision diffuser, condition on both hand and object states but allow ghost states, where the object moves without contact. Ghost states arise because the model can modify object positions freely, violating physics, a problem unseen in fully actuated manipulators but critical for dexterous hands. Our key insight is to design an interaction-aware diffusion planner that, 1. Jointly models hand and object states to prevent ghost motions, and 2. Uses classifier-guided diffusion for flexible goal adaptation at inference time. By coupling hand configuration and object pose in a single diffusion process and adding physics-aware guidance, DexHandDiff achieves physically plausible, goal-adaptive planning for dexterous tasks. Then, I will delve deeper into our approach. The DexHandDiff framework has 3 main components. During training, we learn a joint state action diffusion model that outputs both hand joint configurations and object poses. We also train behavior models, each encoding task-relevant guidance, such as alignment or contact constraints. At inference, we sample noisy trajectories and iteratively apply guided reverse diffusion. At each step, the diffusion model predicts a partially denoised trajectory, and we add gradients from our guidance energy to bias the sample toward physically valid, task-relevant behaviors. The joint state action diffusion model represents each trajectory as concatenated state and action vectors, hand joint angles, object pose, and next hand action. We train this model with a classifier that scores whether a trajectory meets a specified goal, such as a target door angle. During inference, we compute the gradient of the classifier's log probability with respect to the noisy trajectory and add it to the denoising step. Because both hand and object states are denoised simultaneously, object motion cannot occur without physically plausible hand poses. For manipulation after contact tasks like door opening and hammer striking, we employ dual-phase guidance. In the pre-grasp phase, alignment guidance attracts the hand toward the contact point without moving the object, and dynamics guidance enforces physically plausible velocities. Contact is detected when hand-object distance falls below a threshold. In the post-grasp phase, we activate goal-directed guidance to move the object to its target configuration, enforce hinge or contact constraints, and maintain dynamics consistency. This two-stage strategy prevents ghost pushes before contact and ensures realistic object motion after contact. In in-hand manipulation tasks, the object is already in the hand, so we use single-phase guidance. We combine 1. Goal state guidance to drive the object toward a target pose, 2. Active finger motion guidance that encourages all fingers to contribute to manipulation rather than letting some float, 3. Dynamics consistency guidance to prevent unrealistic jerks, and 4. Physical constraint guidance to maintain valid contact surfaces. This combination enables complex in-hand tasks like pen spinning or fine rotations with physically valid interactions. Designing guidance functions manually for each task is time-consuming. To automate this, we propose an LLM-based guidance generation pipeline. First, we prepare a template prompt containing function purpose, guidance structure, pre- and post-contact, environment details, hand and object DOFs, function signature, task instruction, and hints. Second, we use a code generation prompt to produce Pythonic guidance functions. Here is an example of an LLM-generated guidance function for door opening. Subsequently, let's see our experimental results. We evaluate DexHandDiff on adroit hand environments and shadow hand block rotate Z. For both environments, we use a 24-joint shadow hand with 30 DOFs. These benchmarks test both in-domain and goal-adaptive generalization in dexterous manipulation. We first test goal adaptability on door opening. This slide compares 5 baselines, including both classifier-free and classifier-guided diffusion planners, to demonstrate that DexHandDiff is the only method that maintains high success rates when opening doors to novel angles. All other methods either fail or drop to moderate performance on unseen targets, while DexHandDiff remains robust across every goal. Next, we compare performance on multiple dexterous tasks, pen reorientation, hammer striking, and block rotation, each evaluated both in-domain and on new goals. This slide shows that DexHandDiff consistently outperforms all baselines by a large margin in every setting. Here's a qualitative example for goal-adaptive door closing. This slide shows visual results across multiple tasks. Here, in-domain pen rotations, up to 180 degrees, hammer nail drives, full 5 centimeters, and cube turns, 180 degrees, appear alongside goal-adaptive examples, continuous pen spinning, partial nail drives, 2 centimeters, and extended cube rotations, 270 degrees. These side-by-side videos confirm that DexHandDiff generates smooth, physically valid motions whether the goal was seen during training or not. To verify that DexHandDiff prevents ghost object movements, we measure the gap between predicted and actual object poses after execution. This slide shows that DexHandDiff cuts that gap roughly in half compared to the strongest baselines. Next, we ablate our LLM-based guidance pipeline. We compare 1. Human-designed guidance, 2. LLM-generated guidance, and 3. A naive goal-pushing heuristic. This slide shows that LLM-generated guidance matches human-crafted performance nearly exactly, while the naive approach falls far behind, validating that our two-stage prompt process reliably produces expert quality guidance with minimal effort. We then perform a component-wise ablation of DexHandDiff. The result illustrates that removing any single component causes a substantial drop in success, whereas the full DexHandDiff model retains the highest performance, demonstrating that each element is critical. Finally, we assess real-time efficiency. With our 3.96 parameter unit backbone and a 50-step diffusion schedule, baseline inference runs at 5 Hz. By integrating DPM solver++ and command interpolation, we can further boost end-to-end control frequency to 36 Hz. Last but not least, if you are interested in our work, feel free to contact with us. Here are the QR codes about our project page and my personal page. That's all. Thank you.